Hello, in this presentation I will explain the creep and relaxation test in nanoindentation. But first I would like to briefly mention nanoindentation. Nanoindentation is a method used for characterization of the surface at the atomic scales. With the nanoindentation technique, various mechanical properties such as elastic properties, plastic deformation behavior, hardness, and elasticity modulus can be examined. And this method allows for the analysis of the mechanical behavior of a material and by applying a very small load to sample on the surface. The diagram on the right illustrates the measurement of hardness and Young modulus of a thin film. In this case, hardness is a short-range property, while Young module is a long-range property. The measured values of Young modules and hardness are the direct response of the elastic and plastic zone in the intended material. In this case, the response is in a thin film. Then nanoindentation creep testing is method used to examine the time-dependent deformation behavior of a material. This test is performed under a constant load or contact pressure by an indenter. And I explained the experiment method. During the testing process, an indenter is slowly applied to the surface of the material and held under a constant load or contact pressure. Meanwhile, the position of the indenter, the formation of the material are monitored over time. The deformation rate and stress-stress relationship are analyzed to evaluate the creep behavior of the material. And creep tests are used in various fields such as fatigue and durability assessment. These tests help predict how a material will behave and perform under real-life operating conditions. In this picture, the indenter tip is applied to surface with a controlled deformation rate until a predetermined load or depth is reached. After that, contact pressure is maintained at a lower level compared to the initial hardness volume. The applied load detoned with P continuously increase to keep the average contact pressure with a plastic region. This is different from anaxial test where the load is kept constant. And if we were to discuss the difference between nanoindentation and anaxial creep testing, first advantage is micro and nanoscale investigation. This test examines the creep behavior of material surface at micro and even nano scales. This provides more detailed information about the surface properties or surface structure and microstructure of the material. Then precise force control. In this test, the force applied by the indenter can be controlled with high precision. This allows for creep testing at very low loads. This precise control enables more accurate and precise results for studying the creep behavior of the material. Another advantage is local analysis on the surface. And this allows for local analysis at specific points on the material surface. This enables comparison of the creep behavior in different regions. It's useful for detecting surface heterogeneity and understanding variation in local creep behavior. And then another advantage is applicability to thin film and coating. This method These methods are ideal for characterizing the creep behavior of thin film and coating. Creep plays a critical role in the mechanical stability and durability of such materials, and nanoindentation tests are an effective tool for understanding the creep properties of these thin films. And a macro-scale creep test has three stages. First, primary stage, then secondary stage, and tertiary stage. In nanoindentation, we usually observe only primary and secondary stage, and tertiary stage where creep deformation speeds up tower failure is difficult to see. And creep strain rate sensitivity, M, is a mechanism that shows how a material behaves under long-term stress. It tells about the material resistance to gradual deformation. When M is small, it means the material is more resistant to deformation. We can find the value of M during secondary part, and in this test, we use mathematical formula called power law sets, and in equation 1, this is creep strain rate, and this is applied stress, and this is constant, and then this is activation energy for a thermally activated process, and T is temperature, and R is molar gas constant. And where C1 is a temperature dependent material constant. For the nanoindentation creep test with Berkovich indenter, rate and stress can be calculated using their equation as follows. Then where H and T indentation depth and indentation time, and P is indentation load. And finally, M can be calculated by taking logarithms of all sides of equation 1, and M is the and strategies of creep test in nanoindentation. First is constant load hold method. In this method, the indenter is held under a constant load, and the deformation, the material is monitored for a specific period of time. The creep behavior and elastic properties of the material are analyzed during this time. And then constant strain rate. The indenter is programmed to apply a constant strain rate to a material surface. The strain rate determines the rate at which the indenter penetrates the material. Then time-dependent loads. With this method, the load applied to the indenter is changed over time. The deformation rate and creep behavior of the material are investigated under this changing load condition. And last one, relaxation test in nanoindentation. And last one, relaxation test in nanoindentation. In stress relaxation test, the indentar applies a high load to material, causing deformation. The load is then reduced to a lower level, and relaxation of stress in the material is monitored over time. This strategy helps assess the relaxation behavior of the material under a changing load condition. And a maximum force. And last one, relaxation test in nanoindentation. In a stress relaxation test, the indenter applies a high load to material causing deformation. The load is then reduced to a lower level, and relaxation of stress in the material is monitored over time. This strategy helps assess the relaxation behavior of the material under a changing load condition. And the challenge is stress relaxation testing is maintaining a constant depth. In this example, stress relaxation of an acrylic and copper sample were measured. Indentation load rates ranging from 1 to 10 micrometer per minute. And when the target maximum load was reached, relaxation was measured at a constant depth, and relaxation time is 100 seconds. And the test consists of three stages: loading, relaxation, and unloading. During the loading stage, as load increased gradually and the depth increased linearly, the relaxation stage was initiated when the maximum load was reached. During this stage, using the depth control feature of the instrument's closed-loop feedback, a constant depth was maintained for 100 seconds, and decrease in load over time was observed. And the entire test was concluded with an unloading stage where the indenter was retracted from the acrylic sample. As a result, when the indentation are made at lower loading rates due to the creep effect of the material, during the loading phase a larger maximum depth is reached. Both the acrylic and copper samples exhibit a stress relaxation behavior when the position of the indentation at the targeted maximum load is held constant. And for tests with higher indentation loading rates, larger change in load loss were observed during the relaxation stage. These are my references, and thank you for your interest. constant flow holds.